This video is on gravitational potential energy for like an astronomical scale. And we used to know the equation like this, and this doesn't work anymore. Um, the reason is gravitational potential energy, that equation, MGH, pretty much works when you're in this, space, which is right on the surface of the Earth. And so something like that. So as soon as we start talking about a satellite or another planet or something out here, yeah, this doesn't apply anymore. So the equation we're going to be using is gravitational potential energy is equal to negative gravitational constant times mass 1 times mass 2 over the distance between those two objects, mass 1 and mass 2. If there's a big object and a little object, we can say capital M and little lowercase m. So yeah, just as we get started here, can gravitational potential energy ever be zero with this equation? Because you would think G is positive, or I should do it like this, positive. Masses are positive, they're not negative, and distance is positive. So how do you get a zero out of this equation? Could you ever get a positive number out of this equation? Um, and the trick is you can make this really close to zero, and essentially zero when R is really big, right? So like when R is really big, whatever you have up here divided by something really big is really close to zero. So that's when you take this and basically bring it way out here. So when R is really far away. Infinity, we say, when you take R to infinity, when you're at infinity. I should have said it that way. Take this to infinity, and gravitational potential energy is zero. Let's uh let's figure this one out. So, oh yeah, so we have the Earth, and we have the Earth, we have the mass of the Earth, we have the radius of the Earth, and we have a rock that is 7 times 10 to the 6 meters above the Earth, and we are going to drop it. What is V when the rock hits the ground? And so what we're going to do is, oops, use conservation of mechanical energy. E1 equals E2. We're neglecting ignoring air resistance. Do the same thing there. Okay. We'll say this is position 1 and this is position 2. And so E1 is equal to UG plus UG1 plus K1 equals UG2 plus K2. Now we're dropping the rock, so its initial velocity is 0. We'll bring in our term negative G. Let's do big M, little m. The distance between the two from the center of the Earth to the rock is R plus H equals. This is negative G M M. When the rock is hitting the surface of the Earth, it is only a distance R away. And this is M V, the V we're trying to find, squared over 2. Cool. We might as well get this term over here, I think. So let's do that. G M M over R minus G M M over R plus H equals M V squared over 2. But look at this, we can get rid of the little m. And I did not do a good job showing that this is big M. These videos are scripted, but yeah, I don't really spend a huge amount of time trying to work it all out. 6.67 times 10 to the negative 11 is g. The mass of the Earth is actually, sorry, I'm thinking we can also do gm 1 over r minus 1 over r plus h. I don't know if that's going to save us a huge amount of time, but I'm going to try it. So this is 6.67 times 10 to the minus 11 times the mass of Earth, 5.97 times 10 to the 24. We'll do 1 over 6.37 times 10 to the 6. And this is 6.37 times 10 to the 6 plus 7 times 10 to the 6 equals b squared over 2. I could have multiplied everything by 2 as well. Well, 6.67. Let's see if this will save us any time. Mass of the Earth, 5.9724. One over 6.37 times 10 to the 6. Oops. Okay. I'm just gonna double check that I did that correctly. 5.97 times 10 to the 24. That's good to me. Did we get this really big number? Um, and we'll multiply that by 2. Did I use negative 11 on that one? I did. Okay. Multiply that by 2, and we'll take a square root. Okay, I think that's actually pretty good. 80, 91. So, sorry, I had to do this over here. It's 80, 91 meters per second. Now, yeah, if we're asking for speed, which actually this is speed, yeah. So this is the speed of the rock when it hits the ground. Okay, good. I feel good about that. Mhm. Yeah, I think that does save a little bit of time. What I did was I took out a GM out of this thing. So it's 1 over R minus 1 over R plus H. Always, we can try to save time if we, I mean, it's useful to try to save time sometimes. Okay, so yeah, I kind of gave it away here. What we're trying to do is figure out the escape speed. Actually, we're going to figure out the equation for escape speed. Imagine you're on the Earth and you want to get something off the Earth. Okay, let's say you have a rock and you throw the rock into the air, it'll go and it'll come back down, right? And by the scale I'm showing you here, this is not just the atmosphere, this is way beyond the atmosphere. So really a person wouldn't be able to do that. In class, we used the example of the Hulk. We imagined that the Hulk had enough strength to throw a rock and actually get it beyond the Earth's atmosphere. But, you throw the rock up here and it still has gravitational potential energy. So it gets up here with 0 speed, but then it'll come back down. The Earth will pull it back down. Um, there's still an attractive force there. It'll pull it back down. Um, so the Hulk tries harder, right? We said in class, throws it up even more speed with even more speed, and it goes up here, and eventually it'll come back down. So essentially, what we want to do is we want to figure out the minimum amount of speed we need to give that rock such that it finally reaches a point with 0 gravitational potential energy so it does not return. So pretty much to infinity. So somewhere way out here where it does reach 0 gravitational potential energy, which is at infinity, and it's the minimum speed, so we want to give it 0 speed way out here. So we want to get it here so that when it goes, it'll stay out here and not come back. That would be the escape. That would be the speed needed to give it the escape velocity. So let's see if we can do that. Here's position 1 and here's position 2. Let's say E1 equals E2. This will be UG plus UG1 plus K1 equals UG2 plus K2, and we just said that both of these are 0. So this would be negative G M M over R. It's the radius of the Earth, plus M V1 squared, or let's call it V escape speed, because this is what we're trying to figure out. V escape over 2 equals 0. I'll set these two terms equal to each other. In other words, I'll add the GM to the other side. This is V escape squared over 2 is equal to G capital M over R. Capital M, little lowercase m. We can cross out the m's. And so V escape squared over 2 is equal to G N over R. And we'll do V escape is 2G N over R squared. And so the square root, we need to take a square root. Escape speed is the square root of 2 gravitational constant, the mass of the Earth or whatever planet we're throwing the rock from, over the radius, in this case. Um, but you can also use V escape from somewhere in orbit. It would just be R plus H, something like that. Cool. Well, that is the minimum velocity needed to, or minimum speed needed to get away from, um, a planet or something. 2GM, the square root of 2GM over R. That is it.